So folks, take a look at this non-homogeneous linear ODE here with these constant coefficients. We've learned that if we have a non-homogeneous linear ODE with constant coefficients, and if it were homogeneous, meaning equal to 0, that we could solve it using this technique of the characteristic equation, and we could eventually give the general solution to it. Likewise, in our study of superposition, we learned that if we were given one particular solution to the non-homogeneous ODE, and we had the solution to the homogeneous ODE, we could combine the two together to give the general solution to this non-homogeneous ODE. But in that case, we had to be given a particular solution to the non-homogeneous ODE. And what we want to learn in this section is how we can find particular solutions. So in fact, that's our goal. In this section, we find particular solutions to nth order linear non-homogeneous ODEs with constant coefficients. And we use a method called the method of undetermined coefficients for this. And we'll explain that. Rather than giving you the outline of that just yet, I'd rather explain it in a couple of examples, and then we'll give the outline to it. So here we're asked to give the general solution to this linear ODE here, but notice that it's non-homogeneous. So first, we're going to solve the corresponding homogeneous ODE, y double prime plus 4y prime minus 2y equals 0. And we can solve that using our technique of the characteristic equation. In this case, I can't factor that, so I'll have to complete the square. So to complete the square, I'm going to take half this linear coefficient, square it, and add it to both sides. And what I've just built is a perfect square trinomial on the left-hand side, and so it has to factor, and you can verify that. It factors as x or r plus 2 quantity squared, and that equals 6 on the right-hand side, giving me the two roots. R is equal to negative 2 plus or minus the square root of 6. So I've got two solutions to the homogeneous ODE. I know that y1 equals e to the negative 2 plus the square root of 6, t, and y2 equals e to the negative 2 minus the square root of 6, t. Solve this homogeneous ODE here. And so the only thing I need to verify is that these two solutions are linearly independent. And to do that, we would compute the Wronskian. So you could compute the Wronskian of y1 and y2 to verify they're linearly independent. Now that I've got that, I can give the general solution to the corresponding homogeneous ODE. That general solution we usually label as y sub h, and we get c1 e to the negative 2 plus the square root of 6 t plus c2 e negative 2 minus the square root of 6 t, and that is the general solution to the corresponding homogeneous equation. Nothing new so far, folks. Now what we want to do is we want to find a particular solution to the non-homogeneous part. And how do we do that? Well, that's this technique of the method of undetermined coefficients that we want to look at. So I will explain this more as we go along, but what we do is we look at the structure of this right-hand side here. We've got this minus 3t. And we know that any particular solution has to, after we take two derivatives of it and do some linear combination of the solution and the two derivatives, has to have something cancel out to give us a minus 3t. So for example, I couldn't expect y equals the sine of t to be a particular solution to this, because if I take a couple of derivatives of sine of t and do some linear combination, there's no way that things are going to cancel out to give me minus 3t here. And in fact, our guess should incorporate the structure of the right-hand side and any successive derivatives of it that could possibly arise. So the right-hand side, if I were to describe that right-hand side, in this case, is a linear function. And so my guess at the particular solution should be a linear function plus any derivatives that could possibly show up when taking derivatives of a linear function. But the nice thing about a linear function is not that many derivatives show up. Nothing crazy happens when I differentiate a linear function. So my guess for yp, so this is my guess for yp, is at plus b. Let me double check that I've got the correct variable. Yeah, at plus b. Because if I take successive derivatives of this forcing function up here, the non-homogeneous component, if I take successive derivatives, nothing's going to show up other than linear, than the original linear function, constants, and then eventually 0. Now what we'll do is we'll take two derivatives of our guess, enough to plug into the original ODE. So we get yp prime and yp double prime is 0. And now I'm going to plug this guess, this structured guess, into the original non-homogeneous ODE. And if I do that, I have 0, because that was the second derivative of our guess, plus 4, and then we had a, because that was the derivative of our guess, minus 2 times the quantity at plus b, where at plus b is our guess at the particular solution. And when all of these terms interact, we want them to cancel out to give us negative 3t, and in this case I'll put a plus 0 there just as a placeholder. So what I end up with is minus 2a t plus 4 times a minus 2b has to equal what I've got on the right-hand side there. And so you can see what we've got now is a situation where we can construct equations to solve for those previously unknown coefficients. That's why we call it the method of undetermined coefficients. So now we're going to solve for both a and b. Well, we know from the first statement that minus 2at has to equal minus 3. So we get minus 2a needs to equal negative 3. And the second equation tells me that 4a minus 2b needs to equal the constant that I have here, which in this case is 0. So we've got 4a minus 2b has to equal 0. So now I can solve this system of equations. In this case, it's not too hard because I can solve one of those equations independent of the other. But in some cases, you might need to use all of your solving equation techniques that we've been studying over this course. But anyway, in this case, we'll go ahead and solve the first equation for a. And if I do that, I get that a needs to be equal to a positive 3/2. Then we'll plug this into 2. And if I do that, then we get that 4 times 3/2 minus 2b has to equal 0. And now I'm able to solve for b. And we get that 6 minus 2b has to equal 0, or that b is equal to 3. So folks, let's just recap what we did. We started with our guess at the particular solution. This is the method of undetermined coefficients right here, that guess at the particular solution. And that's what the bulk of our time is going to be spent discussing. What should that guess look like in this method? We then took enough derivatives to plug everything into the original ODE and then come up with a system of equations to allow us to solve for those previously undetermined coefficients. In our case, we found that for this guess to work, a would have to be 3/2 and b would have to be 3. So our yp, based on that, is going to be 3/2 t plus 3. Now that we've got the one particular solution, we're back to where we were when we were doing our superposition problems from the previous pre-work. So we can now give our general solution as our homogeneous solution, that's our family of solutions to the corresponding homogeneous equation, plus the one particular solution. But what we're doing better than we did before is we weren't given the particular solution, but we guessed at what it should look like using this method of undetermined coefficients and then found what the coefficients had to be. So our general solution to this ODE is y of t equals c1 e to the negative 2 plus the square root of 6t plus c2 e to the negative 2 minus the square root of 6t. That was our y sub h, plus now our newly found particular solution, 3/2 t plus 3. So just to reiterate, this was our family of solutions to the corresponding homogeneous equation, and this is our one particular solution that we found, in this case using the method of undetermined coefficients. So to point out where we're going to go, in the next video, notice that I've got the same left-hand side to the differential equation, so I won't have to do the work to solve the corresponding homogeneous ODE, but I've got a different forcing function on the right, and we'll talk about what our guess should be using this method. So join me in the next video, and I'll see you there.